All right, hi everyone. Welcome back to section 6.3. And in this video, we're finally going to be able to solve a differential equation of second order using the method of Frobenius. So we are going to solve it about the regular singular point x equals 0. Okay, so when we're solving these singular points, we're just going to focus them around x equals 0. So what does that mean? It means we're going to use the power series solution centered around x equals 0. Okay. It's like, x minus 0 to the n plus r. But this is the type of series we're going to be solving it about. Okay. Centered at x equals 0, about that singular point. So we want to use the Frobenius method because x equals 0 is a singular point. So let's go ahead and get started on that. So here I'll say solution. And so using the method of Frobenius, okay, we try to find a solution of the form that we were just discussing. Y equals the power series centered around the singular point x equals 0. Okay, but it's a differential equation. We're going to need to plug this and its components back into the differential equation. So we're going to need a couple things. We're going to need this first derivative. So the neat thing about these Frobenius method and these singular points is that when you take a derivative, the index actually doesn't shift here. Right? It still says n equals 0, but we still treat it like a power rule. So n plus r times a sub n x to the n plus r minus 1. And we need a second derivative. And same thing, the index doesn't shift here. It's n plus r times n plus r minus 1 a sub n x to the n plus r minus 2. Okay, so the index being the same helps us out quite a bit in the solution process, but just be careful with that. The index doesn't shift here. Okay, so let's go ahead and plug this into our differential equation. Plug y prime, y double prime into the differential equation. All right, so what we would have is 3x times the power series n equals 0, n plus r, n plus r minus 1, a sub n, x to the n plus r minus 2, plus y prime, which is the power series n equals 0, n plus r, a sub n, x to the n plus r minus 1, minus just y. And that's our power series centered at the regular singular point, 0. And then this all just equals 0. Okay, great. So what we want to do now is distribute the 3x. The middle term, there's nothing to distribute, and then distribute that negative. So let's go ahead and do that and drop the brackets. So what we get is n equals 0, n plus r, n plus r minus 1, a sub n, x to the n plus r minus 1. Oh, forgot a 3 in the front. Okay, so the 3 just distributes and the x distributes to this x to the n plus r minus 2, which gives us n plus r minus 1. The middle term, there's nothing to take care of there, so it's just the same. N plus r, a sub n, x to the n plus r minus 1. So looks good. We got the same exact kind of setup here for the first two terms. And then we distribute the negative, and there's nothing really to do there. It's just negative a sub n x to the n plus r, and this all equals 0. Okay, great. So since the first two terms are essentially the same, what we can do is combine them. What I mean by that is they're both starting out at n equals 0. They both have x to the n plus r minus 1. So what we can do is combine them. We can combine those series. So combine, and what we get is the power series n equals 0, 3 times n plus r, n plus r minus 1, a sub n, x to the n plus r minus 1, plus n plus r, a sub n, x to the n plus r minus 1. So that's all one power series. Okay, I'm gonna put some brackets around it just to show that that's one power series. All right, minus the power series n equals 0. Oh, excuse me, plus. It's now plus. I distributed a negative. All right, negative a sub n, x to the n plus r, and this all equals 0. Okay, so got two power series now since we combined. And remember, we're trying to simplify this down into essentially one power series so that we could set up a recurrence relation and find our coefficients and all that good stuff. So we're trying to get this into one power series. So what else can I do? So I notice here that, both of these expressions have a sub n, x to the n plus r minus 1. So what I'm going to do is factor out that a n x to the n plus r minus 1. All right, I'm going to factor that out. And so what I would be left with is the power series n equals 0. Brackets could stay. 3 times n plus r times n plus r minus 1 a sub n. Excuse me, we're factoring that out. Plus n plus r brackets, and we factor out the a sub n x to the n plus r minus 1. Okay, and then our term on the right here is still unchanged. Okay, what else can I do? So there's a bunch of terms inside here, like 3 n plus r times n plus r minus 1 plus n plus r. There's a lot of a little bit of messy terms going on here. So I want to simplify this out a bit. Okay, so let's just kind of bring this down here. And what do they have in common? They have an n plus r in common, right? So I'm going to factor that out. So this would be, oh, I don't know, n plus r, factoring that out, times 3 times n plus r minus 1 plus 1, right? Because I'm factoring out an n plus r out of this whole expression. And, if you distribute in this 3, right, you get n plus r times 3n plus 3r minus 3 plus 1. And so that simplifies to n plus r times 3n plus 3r minus 2. So that looks a lot better than what we have in there. So sometimes these solutions require some algebra to make it look a lot cleaner. I mean, you could work with this, right? There's nothing wrong with it, but it's a little messy in there, right? Like 4 different terms going on. Like we want to condense it into 2 terms is a lot nicer, right? This 3, um, you know, n plus r times 3n plus 3r minus 2. It's a lot cleaner. So yeah, let's go ahead and rewrite what we got. So this would be n plus r, 3n plus 3r minus 2, right? All times a sub n x to the n plus r minus 1 plus the power series n equals 0, negative a sub n x to the n plus r equals 0. So a lot cleaner, a lot smaller too. Okay, the next step that we want to do is factor out, we always want to do this, an x to the r. Okay, so notice for both of our power series, we have x to the r, right? R is a coefficient. Okay, R is going to be a number. It's going to be a root that we're going to find. It's not going to be part of our index, part of our series. So we want to factor that out, and we're going to be able to figure out what exactly R is. We're going to get two roots for R. So we want to factor out an x to the r. So let's do that. So what we will get is x to the r, factoring that out, big old brackets, okay? Series n equals 0, n plus r times 3n plus 3r minus 2, a sub n x to the n plus r minus 1 plus the power series n equals 0, negative n x to the n all equals 0. Oh, excuse me. So we're factoring out an r, so I accidentally wrote r again right here. Apologies. Just trying to make sure I account for everything so I don't miss anything. But yes, we factor out an r, so this is our line right now. Okay. So remember, we want to get it into one power series, x to the n, same index. Okay. So one thing we can do here, because I know I'm going to want to index shift this x to the n minus 1 to get it to look like x to the n, one thing I'm going to do is peel off the n equals 0 term, okay, in this first power series. So I'm going to peel off n equals 0. Okay. This term staying unchanged. We're not doing anything to that. It's perfect. It's x to the n. We don't want to do anything to that. The issue is here. We have x to the n minus 1. We want to get that to x to the n. So we're going to peel off the n equals 0 term. So what this would look like is x to the r, brackets. That means I'm going to plug in 0 wherever there's an n. Okay. So this would be r times 3r minus 2 a naught x to the negative 1. Okay, so I'm just plugging in 0 wherever there's an n. Okay, I'm peeling off the n equals 0 term. Okay, and so now my series starts at n equals 1. Okay, and let me just copy down the rest of this line. All equals 0. Okay, good. So remember, we want to have the same index. We want to be x to the n. So I have x to the n minus 1 here, and I have n equals 1. So the perfect way to kill two birds with one stone is index shifting, all right? So if I index shift, this n equals 0, n equals 1 would go to n equals 0, and this would go to just x to the n. Okay, so let's check that out. So we're going to index shift, okay, index shift, we're going to get n equals 0 and x to the n. Okay, so if I index shift, what I would get r times 3r minus 2 a naught x to the negative 1. My index will now start at 0, but I would need to add 1 to every single n in my series, right? If I subtract 1 from the index, I got to add 1 to every series. So what I would end up with is n plus 1 plus r, 3 times n plus 1 plus 3r minus 2, a sub n plus 1, x to the n, plus 1 minus 1. And then this power series just stays the same. We haven't done anything to it at all. Okay. So that's us index shifting. And it works out great because what we end up with is exactly what we want. Power series n equals 0, n plus 1 plus, well, let me rearrange this. That's a little awkward. I'm going to do n plus r plus 1. If I distribute in that 3, right, I get 3n plus 3 minus 2, which would just be 1, a sub n plus 1, and then just x to the n. All right, so it works out great. Okay, so now I have two series, both starting out at n equals 0, and both are x to the n. So what can I do now? I can combine them. Okay, so we know how to combine them. We've done it in the solution already, but we're trying to clean it up. So what I'm going to do in the same stroke is combine and factor out and x to the n. So I'm going to factor out an x to the n out of both of them. So let's do that. So let me kind of, annotate that we're combining these two and we're going to factor out an x to the n. So what we end up with is x to the r brackets r times 3r minus 2, a naught x to the negative 1 plus the power series n equals 0. All right, we're factoring out an x to the n. So just rewriting my terms down, a sub n plus 1 minus a to sub n, all times x to the n, all brackets equals 0. Okay, so we combined all this into one power series, n equals 0, x to the n. Okay, so that's a lot of our work went into getting to this part right here. So now that we're at this one power series mark, this implies, right, that all these things equal 0, right? X to the r times all of these terms equals 0. This implies that r times 3r minus 2, a naught equals 0, and n plus r plus 1 times 3n plus 3r plus 1 times an plus 1 minus a sub n equals 0. Okay. But note, we have A naught here for our sort of our equation. You know, we want to figure out what R is essentially. And the reason why we're able to do that is because nothing is gained from that A naught equaling zero. So we must have that R component, R times 3R minus 2, that must equal zero. And these are going to give us our roots. Okay, so we would have R equals zero and excuse me, 3R minus 2 equals zero. So we would have R equals zero and R equals 2/3. So these are our what's called initial roots. Okay, so these are a part of our solution. They give us our two solutions, and eventually we're going to learn a quicker way to see what these roots might be. But for now, like we're able to find them within the problem. Okay. But yeah, these are our roots that give us our two solutions. So we're going to have one solution, two solutions. Okay. But we'll keep these handy. We got to set up a recurrence relation first. Okay. So let's go ahead and keep moving with that. And for our recurrence relation, remember we want to solve for the bigger an, so we want to solve for an plus 1, and we're going to move everything over to the right side. So what we would get is an plus 1 equals an all over n plus r plus 1 times 3n plus 3r plus 1. Okay, and then our index starts at 0, 1, 2, dot, dot, dot. Okay, so this is our recurrence relation. Okay, starting out at n equals 0 because that's just where our index is starting out at for our power series. Okay, so we have this recurrence relation, but here's a little bit of a different component when we're dealing with these Frobenius method and singular points. It's that we need to substitute in r equals 0 and r equals 2/3 individually into our recurrence relation. So we're going to substitute into this R, this 3R. And we're going to get two different recurrence relations. That's going to give us two different power series. So let's write that down. We then need to substitute R equals 0 and R equals 2/3 into the recurrence relation to get two different recurrence relations and two different solutions. Okay, so that's the goal. That's where we're getting our two solutions from. So let's go ahead and get started with that. So you know, for, let's call R1 2/3. All right, since it's the actual number, if I plug this into my recurrence relation, plug it in wherever there's an R, what I get is a sub n plus 1 equals A sub n all over looks like it would be 3n plus 5 times n plus 1. Okay, so that's what I would get for when I plug in equals 2/3 and for R2, we'll make that just a 0, 1. I'll get an plus 1 equals a sub n all over n plus 1. Doing the math in my head, sorry. 3n plus 1. Okay, so I'm just plugging R equals 0 into this. Okay. All right, sounds good. So let's go ahead and keep moving. Those are my two recurrence relations. So we got to go out and find what the power series solutions would be for these. Okay, so these are my two recurrence relations. I'm going to go ahead and box them up. All right, so let's do our first one. So here I'll say like 1, for R sub 1 equals 2/3, right? We get the recurrence relation. I'm going to rewrite it again so it's a little accessible to us. 3n plus 5 times n plus 1. Okay, and we are just going to go out and get some constants. All right, so for n equals 0, okay, what we get is a1 equals a0, a naught over 5. Okay, then I'll just go ahead and box that up. Now for n equals 1, all right, for n equals 1, I get a2 equals a1 over 16. If I plug in n equals 1 into there, and that's what I get, but I can go ahead and plug in, I know what a1 is a naught over 5, so I could substitute that in for a1. So I get a naught over 5 over 16, which is a naught over 80. So that means a2 is a naught over 80. Okay, so let's do one more, I guess for good measure. Let's get a3. So n equals 2, I get a3. That would be a2 over 33. Okay, so that would be a naught over 80 over 33 is going to be a big number. I remember I could just plug it in for a2. So I get a naught over 2,640. That's a big number. So, a3 equals a naught over 2,640. I think the number's gonna get really big after that, so let's just go ahead and stop right there. I think that's good enough. And so we'll do the same thing for r equals 0, okay? And just remember, that this is for, n equals 0, 1, 2, dot, dot, dot. So we're gonna do the same thing for r equals 0. So let's go ahead and try that out. So, step 2, or recurrence relation 2. for R2 equals 0, what's our recurrence relation? It's a sub n plus 1 equals a sub n all over n plus 1 times 3n plus 1. Okay, so let's start plugging in some indexes. So for n equals 0, right? If I plug in n equals 0, I get a1 equals a naught over, looks like it's just going to be 1. So, I guess we could say a1 equals just a naught. Simple. Okay. So now for n equals 2, excuse me, n equals 1, I get a2 equals a1 over, looks like it would be 8. Okay, but a1 just equals a naught. So that means it would be a naught over 8. So a2 is just a naught over 8. Okay, a nice simple number so far. So n equals 2. Let's just get a3 like we did like the last one. This would be a2 over 21. Okay, but I know a2 is just a naught over 8 divided by 21. So yeah, we're going to get a slightly bigger number. So this would be a naught over 168. So yeah, a3 is a naught over 168. Okay, so I have some values here. I have a naught, a1, a2, a3 for both of these recurrence relations, and we're able to get two series solutions now. So let's kind of wrap this up now. Okay, so solution, right? All of our solutions for this Frobenius method are, you know, of this form, x to the r, n equals 0 to infinity, a sub n, x to the n. Right? Maybe it isn't that way at first, right? We start off with x to the n plus r, but remember we factored out like x to the r within our process. That's the same solution. So really, we have a solution like this. And the recurrence relations give us what this component is, the power series, in terms of n. So that's what we have, right? And if we expand this, we get like x to the r times a naught plus a1x plus a2x squared, etc. Right? So we're going to get two of these solutions. So our first y1 is going to be x to the 2/3 times a naught plus a1x, but a1 was what? A naught over 5. A2 is a naught over 80. A3 is a naught over 2640. So let's go ahead and plug those in. A naught plus a naught over 5 plus a naught over 80. Excuse me, forgot the x here. Let me rewrite that. A naught over 5x plus a naught over 80x squared plus a naught over 2640x cubed. And we stopped there. So we can put dot, dot, dot. All right, that's our first solution for our first recurrence relation. And now let's do the second one for when r equals 0. So that means y2 is going to be x to the 0, a naught plus, what are our terms? A1 is A naught, A2 is A naught over 8, A3 is A naught over 168. So this would be just A naught X plus A naught over 8X squared plus A naught over 168X cubed plus dot dot dot. Okay, so these are our two linearly independent solutions, but they're kind of ugly, and we even have like an x to the 0 here. So I don't know, like x to the 0 is just like 1. Um, we could factor out an A naught for both of these and just let A naught equal, different constants, right? It's just a constant and they're different constants. So it could be like C1, I don't want to say equal, but C1 and C2. So the general solution could be y equals C1 x to the 2/3 times 1 plus 1/5 x plus 1 over 80x squared plus 1 over 2640 x cubed plus dot 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 plus C2, x is 0 is just 1, so it's just C2, 1 plus x plus 1/8 x squared plus 1 over 168 x cubed plus dot dot dot. And that's my solution. I have my two power series of this form. Two of them, both linearly independent, and that's my answer. Okay, so these power series solutions are a lot of work, especially this Frobenius method. It's a little bit extra with the initial roots and the undetermined coefficient, but it's essentially how you do it, all right? It's the game plan's still the same, you know, kind of your goal is to get into one power series, x to the n, and then set up your recurrence relation. And a little different, you're going to get two of them with two different roots, but it's the same idea. So yeah, long video. Thank you for staying with it. Hopefully it made some sense. But yeah, thank you for watching, and I'll see you in the next video. Take care.